Good evening. We are Group 9 of ESTR 2020, and today we'll present our work on low-rank Bayesian logistic regression. We compare two inference methods, Markov chain Monte Carlo and Laplace approximation, for high-dimensional Bayesian modeling. Let's dive in. Our goal is Bayesian logistic regression for binary classification, where its parametric form are as shown on screen. Note that the matrix A is factorized into U times the transpose of U, limiting its dimensionality and degree of freedom. The distribution of our prior are Laplacian for U and gamma for beta prime. The likelihood for labels Y given features X is the bottom equation. This reduces dimensionality while preserving interpretability. The Bayesian posterior involves integrating over 100 parameters, which is computationally intractable. We address this with two approaches. One, MCMC, which samples from the exact posterior via random walks, and second, Laplace approximation, which fits a Gaussian around the MAP estimate. Both methods avoid direct high-dimensional integration, trading accuracy for efficiency. For MCMC, we use the Metropolis-Hastings algorithm. We propose a Gaussian random walk with tuned step size, resampled by the variance. And by adjusting the step size, we achieve an acceptance rate of 25% during short exploration without stagnation. After burn-in and thinning, MCMC ultimately achieves a 60% test accuracy. However, it is computationally expensive due to the repeated likelihood evaluations in high dimensions.
Now let's use another method, Laplace approximation, whose main purpose is to find a normal approximation QZ that is centered on the mode of the FZX. Just like the graph here, FDX is what we desire, and QZ is our estimate. To use Laplace approximation, we should first find the mode, which is the MAP point of the log posterior. Here we choose k equals 1 for simplicity and combine u and beta to construct a n+1 dimension vector theta. Since we cannot obtain a closed form solution, we use the stochastic gradient descent to converge to the optimal. Then we'll approximate log posterior via second-order Taylor expansion around the MAP point. We compute g theta d and integrate it to get z, which is the denominator of the Bayesian formula. Then, for a new point x star, we'll integrate and calculate the predictive probability, which is still hard to compute. Finally, we use a Mackay approximation to get the closed form probability and predict y based on it. So here is our result. We can see that the test set accuracy is 56.5%. Now let's summarize the comparison between MCMC and Laplace approximation from three aspects. First, predictive performance. Both methods achieve a similar accuracy. MCMC reaches about 60% and Laplace 56.5%. The relatively low accuracy may be due more to model or data limitations than the inference method itself. However, MCMC tends to better capture uncertainty when tuned properly. Second, approximation fidelity. MCMC samples directly from the true posterior, making it more reliable, especially when the posterior is good or complex. In contrast, Laplace assumes the posterior is Gaussian, which can miss important features like asymmetry or multimodality. Third, computational cost. MCMC is much more computationally intensive, requiring many samples and full likelihood evaluations. Laplace is much faster, only needing a single optimization enhancing computation, making it more scalable. So, MCMC offers better fidelity, while Laplace is more efficient. That's all for our presentation. Thank you.